All right, so in a previous video, we took a look at Taylor polynomials and found out what they are. And they are simply a way of using a polynomial to approximate a difficult type of function, such as a trig function or exponential functions with e to the x, or we could use logarithmic functions. Lots of different ways that we can use these Taylor polynomials. And we do that because polynomials are much easier to work with than sometimes these trig functions for approximating values at a particular point on a function. And so we can use this sine of x approximation. And remember, this is an approximation because it's a Taylor polynomial, which means it has a particular endpoint right here. If we took this polynomial and put a dot, dot, dot at the end of this, that means it would go on forever, which would indicate it's a Taylor series. And if it is a Taylor series, it is no longer an approximation of sine of x. It actually is the sine of x. And so what we're going to do with this particular function right here is we are going to take this and figure out what the Taylor polynomial for cosine of x is using derivatives instead of using the same method that we did for deriving this polynomial for sine of x. We could use the same method that we did for sine of x, but a derivative is going to be much easier in this situation because remember, when you have an equation, if you take the derivative of the left side of your equation, that's okay to do as long as you take the derivative of the right side as well. And so that's simply what we are going to do on this. And so what that is going to generate on the left side is going to give us cosine of x. And then on the right side, you're going to have the derivative of x, which is 1, minus. Now let's think about the derivative of the second term. The denominator is 3 factorial, which is 3 times 2 times 1. And if you take the derivative of the numerator, that is going to give you 3 times x raised to the second power. Now, the 3's are going to cancel with each other, and that is going to leave us with x squared over 2 times 1, which is 2 factorial. All right, so now we're going to have plus, and if we do the same thing on this next term, when you bring the 5 to the front for the derivative, this 5 will cancel out with the 5 in the factorial, which is going to leave us with x raised to the 4th over 4 factorial. And this process would continue on and on. The signs do still alternate, so you're going to have negative 1 raised to the n. And when you take the derivative of this term right here, if you bring the 2n plus 1 to the front, remember that, let's write this out as a factorial on the bottom for a second. 2n plus 1 factorial would be 2n plus 1 times, and then the next lowest number, we would subtract 1 from this, which would leave us with 2n, and then the next lowest one is 2n minus 1, and that continues on. So if you think about taking our derivative here, you're going to bring this 2n plus 1 to the front, which will cancel with this 2n plus 1, leaving us with 2n factorial. All right. And subtracting 1 from the exponent is going to leave us with x raised to the 2n. over 2n factorial. All right, so what we have now is we have the approximation for cosine of x. This is the Taylor polynomial for cosine of x. All right. So differentiation isn't the only way that we can turn Taylor polynomials from one function into another. We can also use substitution. All right. Take a look at how we can use substitution to evaluate this. Find the 8th degree Taylor polynomial for y equals cosine of x squared by substituting x squared in for x in the y equals cosine x polynomial. And so this is your cosine of x Taylor polynomial. If we want to find the Taylor polynomial for cosine of x squared, all we're going to do is take x squared and replace it everywhere we see an x. All right, so we're just substituting x squared in for the x. All right, so what that's going to generate then is going to be your 1, there's no variable there to substitute in for, minus, and then when you substitute x squared in for x, that's going to give us x squared squared over 2 factorial plus x squared to the 4th power over 4 factorial minus x squared raised to the 6th power over 6 factorial plus, and it continues on, negative 1 to the n, and this would be x squared raised to the 2n over 2n factorial. All right, since the question asks us to find p sub 8 of x, what this means is an 8th degree polynomial. What we're going to do is cut off the polynomial at 3 terms because this term, if you multiply your exponents here, gives you x to the 8th. That is our 8th degree Taylor polynomial. All right, so what that comes down to then is going to be cosine of x squared is approximately 1 minus x to the 4th over 2 factorial plus x to the 8th over 4 factorial. And once again, this is a Taylor polynomial centered at x equals 0, which makes it a Maclaurin polynomial. All right, so now let's come up with the Maclaurin polynomial for f of x equals 1 over 1 minus x. We could actually do long division with this rational function to obtain the following. All right, so let's go ahead and work this out. All right, so long division, you're going to be taking 1 and dividing it by 1 minus x. All right, so we're going to put some extra terms on here. 0x for a placeholder, 0x squared, 0x cubed, and so on. We don't need to do all the division to find the pattern here. We're going to see it pretty quickly. And so the long division, what you're trying to do then is going to be to figure out 1 multiplied by what will give us this first term, and that will be a 1. And then you multiply that 1 by the 1 minus x, giving us 1 minus x. Draw our line and subtract. That gives us a positive x, bring down the next term, So then we repeat the process and try to figure out 1 multiplied by what will give us this first term. And that is going to be a positive x. And so multiplying, that will give us x minus x squared. Subtracting this will give us x squared. Bring down the next term. And we repeat the process. 1 multiplied by x squared will give us x squared. And then x squared times negative x gives us minus x cubed. Parentheses, and subtracting gives us x cubed. Hopefully you can see the pattern here. This is going to continue on with x cubed, x to the 4th, and so on. All right. So what that tells us in is that 1 over 1 minus x is approximately 1 plus x squared plus x cubed plus dot 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 x to the n. All right, so what we're going to do now is we are going to use that Taylor polynomial that we just found, and we're going to find Taylor polynomials for some variations of that. All right, starting out with 3 over 1 minus 2x. All right, so what we can do, we can think of this as 3 over 1 minus 2x. And the 3, let me actually write it this way. We can think of this as 3 times 1 over this. Now, what we can see then is that what we're going to be doing is replacing this x right here with 2x. And that puts us in the same format, 1 over 1 minus x. And then we're going to take that and multiply every term by 3. All right, so let's go ahead and do this. If we replace this first term, well, there's no x to replace, but there is a 1 that we can multiply by this constant, 3. All right, so what that's going to give us then is 3 plus, all right, so now we're going to replace this x with 2x, and then we have to multiply by 3, which will give us 6x. All right, now we replace this x with 2x. And if you square 2x, that's going to give you 4x squared, which we then multiply by 3, which will give us 12x squared. And we are looking for a third order Maclaurin polynomial. Third order is a little bit different than a third degree. Third degree means we're looking for the degree to be 3. Third order means that we want 3 terms. All right, so this is a third order Maclaurin polynomial for this particular function. All right, so the next one we're going to treat kind of the same way. And so what we can do with this is we can say this x in the numerator, we're going to multiply it by our polynomial. Now in our denominator, we have 1 plus x, and that would be the same thing as saying 1 minus negative x. And we do that because we've got to get it into this format right here, 1 over 1 minus something. So in this case, that something is going to be negative x. That means wherever we see an x, we're going to replace it with negative x. And then we multiply the whole polynomial by x. All right, so in our first term, we do not have a variable to replace, but we can multiply it by this x. And so that gives us our first term of x. Now the second term here, we can replace this with negative x, and then we multiply it by x. And so that's going to give us minus x squared. Now the next term we replace with negative x, and so if you square a negative x, that will give us positive x squared, which we then multiply by this x, which will give us positive x cubed. All right, so that will be our third order Maclaurin polynomial for this particular function there. All right, so the next one, again, we need to manipulate this a little bit. So the 4 in the numerator, we can bring that out in front and think of it like this. Now the 2 minus x, keep in mind what we need is a 1 right here. And so in order to make this a 1, we need to factor 2 out of both terms here. All right, so if we factor a 2 out, that's going to leave you with 1 minus 1/2 x in your denominator. All right, so when you multiply, well, the 4 and the 2 are going to reduce, and that becomes 2. And so what we have now is 2 times 1 over 1 minus 1/2 x. This 1/2 x will get substituted into the x in your polynomial up here, which we will then multiply all the terms by 2. All right, so let's go ahead and do that. Substituting, well, in the first term, you've got a 1, so there's nothing to substitute in, but we will multiply it by the 2, which is going to give us 2. All right, so then we have the 1/2 x gets substituted in here, which will be a 1/2 x. And when you multiply that by this 2, becomes simply x. All right, so the next term, we're going to put 1/2 x in right here. And so what that's going to give us then is going to be 1/2 x squared, which we will then multiply by 2. Now what that becomes is 2 times 1/4 x squared, which will be 1/2 x squared. And that is our third order Maclaurin polynomial. All right, so another thing that we can do besides taking the derivative of both sides to find some other Taylor polynomials is we could also integrate both sides of an equation to find some more Maclaurin polynomials. All right, so let's think about integrating both sides of this. If you integrate the left side, then what you're going to end up with is going to be the negative natural log of 1 minus x equals, now the integral of the first term is going to be x, integral of the second term will be x squared over 2, the next term x squared over 3, x to the 4th over 4, dot plus x to the n over n. Now the other thing that we need to do is we need to get rid of this negative. We can do that by dividing the entire equation, and that's going to give us natural log of this is equal to negative x minus x squared over 2 minus x cubed over 3 minus x to the 4th over 4 minus dot 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 x to the n over n. All right, so let's see how we can use this particular function. This says, let's use this polynomial to approximate the natural log of 0.3. Now, 0.3 is what we're trying to find the natural log of, and that would be a calculator question normally, but we can get a pretty good approximation of it by using our Taylor polynomial here. And so if we want to take the natural log of 0.3, that means the x value needs to be 0.7, because natural log of 1 minus 0.7 is 0.3. All right, so substituting that in is going to give us negative 0.7 minus 1/2 times 0.7 squared minus 1/3 times 0.7 cubed, which comes out to approximately negative 1.059. So in summary, many functions can be approximated by polynomials. In particular, we found formulas for Maclaurin polynomials of arbitrary degree for sine of x, cosine of x, 1 over 1 minus x, and the natural log of 1 minus x. Keeping in mind that we can modify any of these to get an infinite number of different polynomials. And we have identified 3 major characteristics of these approximators. Number 1, they are perfect at the center. So if it is a Maclaurin polynomial, then the center is going to be at x equals 0. Number 2, their quality decreases as you move away from the center, but the third quality is that their quality improves as you include more terms in your polynomial. And finally, we saw that there are several ways to generate new Taylor polynomials from the known ones. Number 1, we can differentiate or integrate both sides of the equation, term by term. Number 2, we can substitute more complicated expressions in for the x. And number 3, we can manipulate the polynomials algebraically.